and welcome to everybody and for this session. I'm going to talk about this continual learning of natural language processing task. So this is mainly a machine learning kind of talk, and I'll be using natural language processing task to present the techniques which is used in this continual learning. Sometimes we also call it lifelong learning. So in the traditional machine learning, we have this sort of isolated single task learning paradigm. When we have a task T, and we have a data set D, and then we have a learning algorithm, and then that learning algorithm produces a model, and the model basically goes to application. And so this is like a waterfall. I mean, just basically a straight line to go to the application. So what is the weakness of this particular paradigm? This is the classical paradigm. There's a few problems. Actually, there are more problems, but I will just list a few which we are trying to address. The first one is the closed world assumption, which means there's nothing new. Okay, when you learn something and when you test your model in the application, you don't see anything new, which also means whatever you see in the real application have been seen in training, and which is not really true in real world, because the real world are full of unknowns and the novelties and the things which are out of distribution. So when we talk about open world, it basically means that's something which we have never seen before, and how do we handle that kind of situation? How do we learn those novelties, which essentially is called open world continual learning. And also in this classic model does not have this continual learning capability. So which basically means there's no knowledge accumulation, there's no transfer of knowledge from one domain to the next domain, or from many domains to the future domain, and from future domains to the past domains. And another thing is that there's no learning after deployment. So you can see in this case, when the model goes to the application and nothing comes back, okay, it's basically it's the one. So it's a one direction. So it's essentially the one direction. There's nothing come back. So we want to make this sort of deployment time sort of active, which basically means we want a system to detect things and also to learn things which are never seen it before. So here is an example of chatbots. So we want the chatbot to learn continually after the chatbot is being deployed. So during chatting, and people can say anything, and obviously there are many aspects of many things which the chatbot does not understand. So then in that case, we should allow the chatbot, we should also enable the chatbot to learn new knowledge and also new language expressions. For example, you may not know what is the birthday of a certain person, and that means a piece of new knowledge. But sometimes you don't really know how to understand a particular expression. Okay, for example, I ask you to switch off the lights. You may not know what do I mean by switch off. And in that case, you should try to ask me and ask the current user or the other users, so you can learn some new knowledge. And so next time when I or somebody else say similar things, and you will have no problem. So this is basically what we humans do, right? And we do learn a lot of stuff during our daily conversations, and we also want to make the chatbot to do the same thing. And we don't want to let the chatbot to rely on the engineers to basically fit the knowledge and keep training this thing and periodically. So can this make the system to learn by itself and continually? Okay, continually. So let me first define what do we mean by lifelong or continual learning. And the lifelong learning was the name which was called many years ago, but in recent years, and most people call this continual learning. So the classical definition of lifelong continual learning is basically like something like this. It learns a sequence of tasks, and T1, T2, Tn, and then continually and then incrementally. And each task has a training data set, okay, a training data set, which has the data itself and also the class labels. So we're talking about this is a supervised setting. So what is the goal? The goal is that we want to learn this task incrementally. That's basically the next one we want to learn will be n+1. Okay, n+1. I learn it incrementally. and we don't want to forget the things we learned before. Okay, and especially in the neural nets, when you learn something, and if the network already have some knowledge, and if you learn something new, you're going to destroy you're going to update those parameters, and when you update those parameters, you're going to destroy some knowledge you learned in the past, which of course will result in accuracy degradation for some previous task. Sometimes all the tasks, sometimes some of the tasks. And we also want to achieve knowledge transfer. And since we have really learned many tasks in the past, can we make use of those knowledge to make us learn the next task better? And also we want to do backward transfer, means we learn this new task, can we sort of improve something we have learned in the past? Okay. So what is assumption? Assumption here, of course, is we assume the task and the data, okay, are both given by the user, okay, and also we assume the task once learned, you will not be able to see that data anymore. Okay, so that's why we call it incremental learning. So when you learn the task n tn plus 1, you will not be able to see the data from T1 to T2 up to Tn. But of course, in the new paradigm, and sometimes we also allow you to save a little bit of data, not all the data, okay? Because we want this becomes an incremental process rather than a multitask learning kind of a process. We want to learn quickly when you have a new task to learn. So here is the kind of a new definition. I give a new definition, and the new part is essentially the orange lines. So the traditional one is still at the top. We can see we have the task T1, T2, Tn, and Tn plus 1. And this is the Tn plus 1 is the new task, and which basically goes to get this data set, and then go to the learning algorithm, the learner, and then you have this knowledge base. You learn something, you put it in the knowledge base, and knowledge base can fit back to the new task. So maybe there's some knowledge in the past which can be used for this new task. Then this new task produces a model, and the model goes to application. And now we see these three orange lines. So during the application, and this model may detect something which is unexpected. And for example, you are a self-driving car, you detect something you never know, you've never seen it before. So in this case, essentially we're trying to detect novelties, and that serves a new task we need to learn. For example, you have seen many things in the self-driving car kind of scenario. Now you see basically a cow, for example. You've never seen it before. A cow is walking on the road, and then now you detect something new, and then you want to learn that stuff. And obviously, in this case, you need to interact with people. You probably don't know what the name of that animal, and then people may tell you, "Oh, that's a cow." And then, so in this process, you collect this ground truth training data, and that is the second orange line. So data gained in application, and that becomes the training data. Then you learn this this new animal, and then basically go through this whole process. This is essentially the new task you learn in animal. So you can see this. We got this closed loop. So you can discover knowledge yourself, and also discover the new task, and discover the data, ground truth training data. Okay, this is all through interactions. So some part of the knowledge you gain from the application, you may also put into a knowledge base for future use. So this is also the terminology we use is called learning on the job, or sometimes we call the learning after deployment. So after you deploy the application, deploy the model in the application process, you learn some more. So this is just like human learning on the job, and you get some training, formal training, for example, in schools, you have some training courses, and then you go to work on the real job. And during the process, you probably hit some problems, you don't know what to do, and then you learn by yourself. Okay, by yourself, with the help with some other people or some other automated systems. So we want this thing become a complete closed loop system. So what are the characteristics of this open world continual learning? Obviously, we want to learn continually and incrementally, and we want to accumulate knowledge, and we want to have this knowledge transfer and adaptation. So we're going to talk about adaptation later on. So the key part is learning on the job. So also we say learning after model deployment. So you just have to be self-motivated, self-initiated, and active kind of activity or process. So the main step involved will be to detect something you have never seen before. So this is also called novelty detection or out of distribution detection. And when you detect something new, this serves as the motivation or also as a new task. And then you try to acquire ground truth training data. For example, you can ask people, what's this? Okay, then people may tell you, oh, this is a cow. And then you basically got the class label of this thing, and then you can learn to recognize cow. So next time when you see the cow walking on the road, you'll have no problem. Okay, no problem. So the final step, of course, when you get this, you take some picture of the cow, and then you also know the name of this cow, the name of this animal, and then you can do a continual learning. So let's talk about this continual learning. So we're going to talk about the classical part, not talking about this the orange part yet. We're going to talk about in the later part of this talk. Okay, it's part of this talk. So continual learning has two major setups or settings. One is called class incremental learning, another one is called the task incremental learning. And I'll be talking about some theoretical stuff about this, especially the class incremental learning. So I need to give some kind of scenario and what do we do. So as I say, just now I said the continual learning basically learns a sequence of tasks incrementally. And when we have the neural nets, normally we learn everything, all the tasks in the single neural nets. Okay, and each task consists of a set of classes to be learned, which is a supervised setup. Of course, we can also do unsupervised setup. Later on, we're going to talk about what happens if it's unsupervised, and basically it's the same thing. Okay, not a lot of difference. So we know the challenge is catastrophic forgetting and knowledge transfer. How do we sort of not forget past when we learn something new? Okay, because we don't really have the data of the past tasks, and then this cause problem was forgetting. So what is the class incremental learning and what is the task incremental learning? So class incremental learning is something like you build a single model and you keep learning more and more into this model. For example, today I learned to recognize chicken and the pig. And tomorrow I need to learn, and probably I hit some other animals. I learn the lamb or let's say sheep. Okay, I learn sheep. So now I have three classes, three kind of animals I learn. So now at the test time, I can say, okay, and I give you an animal, you tell me whether it's a lamb, is a chicken, or is a pig. Okay, so in this case, at the test time, you don't really know when did you learn the first two animal and when did you learn the second, the third animal. So essentially, we say there's no task-related information during testing. Okay, essentially, you incrementally learn more and more animals, for example, in this case, to recognize more and more animals. So the task incremental learning means you learn each task basically as a separate model. Okay, essentially, let's say today I learned this task about sentiment classification. Okay, tomorrow I may learn something like I'm going to classify political articles into different classes. So these two tasks has nothing to do with each other. Okay, so at the test time, when you're giving me an article, you want me to tell you, is this sort of sentiment analysis, or is this sort of one of those political science kind of articles? Then you have to tell me which model you want me to use. Okay, so in this case, you need to provide the task ID. So you can see the second setting of the task incremental learning is much easier because you can build the model separately. And then in the neural nets, you can protect it. And then you can keep learning more and more because they don't really interfere with each other. But in the class incremental learning, this is very challenging because they interfere with each other. And then because you don't really have a task-related information. So formally, mathematically, definition is very complicated, but I hope you get the point. And mathematically, definition and CIL or TIL looks like this. And this is very complicated. So this theoretical paper basically says we want to find some find some things we know how to solve this problem called CIL. TIL is relatively easy because you learn something, you just protect it, and then so you learn the next, you're not going to destroy what you learned in the past. But in the CIL, you definitely will destroy, not necessarily destroy, but at least make the previous things you learned will not be so effective. Okay. So the theoretical result essentially says we identify and also prove a necessary and a sufficient condition for solving the CIL problem. Okay, what is this necessary and a sufficient condition to solve this thing? And then based on this theoretical result, and we also design some sort of practical algorithms, and then we show this algorithm does better than the existing baselines. Okay, so and what this thing is trying to do, essentially, we try to, based on this definition, and we try to decompose this problem into two subproblems. The first problem is within task prediction. So when you learn this particular task, you want to make sure your within task this prediction is classification is actually very accurate. Okay, and then you don't really know when you come to the test time, you don't really know which task you were doing. Okay, you're doing. So then we also have to have a task ID prediction. Okay, task ID prediction. Okay, so this is of course is obvious. Okay, it's obvious. Now mathematically you can write it this way. You can say it's essentially in the within task the times this task ID prediction. The second part is the task TP. It's called task ID prediction. And then we also prove task ID prediction is essentially the same as out of distribution detection. So what that means is detecting novelty. Essentially, it's the same problem. Okay, because they bound each other. And then we say, oh, now in this case, we can sort of use the out of distribution detection, novelty detection. Okay, essentially, out of distribution and novelty detection is the same thing. We can use the novelty detection to perform this task. Okay, so we say this is this within task prediction and the out of distribution detection are necessary and sufficient conditions for CIL. Okay, and then we have some techniques. So we say, okay, if that's the case, okay, then we basically design a simple algorithm which essentially does this. Okay. So for the first part for within task prediction, we basically build any model, and then we use some mechanisms to protect it, to make sure we don't forget. Okay, just now we talked about this task incremental learning, and we can protect the models, and then you learn more and more, and you don't forget the past. However, we can't just use protection because we still want to do the ID prediction. Okay, ID prediction. So instead of doing ID prediction and based on theory, we say we can do OOD detection. Then that's good because there are many OOD detection algorithms. Okay, many detection algorithms, and some of them are very strong. Okay, very strong. So in this case, we're using CSI. This is a particular algorithm which was published 2 years ago, and with this protection, and then with this sort of out of distribution detection, we essentially have these two algorithms. One is called HAT plus CSI. HAT is one of those algorithms which can protect what you have learned in the past. And the SOUP is also one of those algorithms, one of those effective algorithms to protect what you have learned in the past. So for both of those guys, if we add CSI, and we can produce a much better result compared to the existing existing baselines. And you can see lots of baselines at the bottom. The green part is our and basically is our system's results with some was little plus C, which basically means some sort of calibration. Calibration can do a little bit better. So then let's talk about a continual learning of sentiment classification. So this is a natural language task. Okay, this is natural language task. And then we also talk about how do we continue to learn a language model. Okay, we can try to improve language model continuously. Okay, continuously. And so this is the sentiment classification. Essentially, when we have a reviews, and for example, I tell you I liked iPhone. And essentially, he says, you basically have to tell me this is the positive or negative about the iPhone. Okay, this is called the aspect sentiment classification. So this is why this thing is useful, because in real life, for example, in a store, for example, Best Buy, you sell so many products, right? And different products have different reviews. You want to continually learn the review of each, learn to classify the reviews of each product. And you can't learn them together because they're different. And you don't want to build an individual model, separately, because just for example, this Best Buy, the sales are, I think they sell 1,000 over category of products. If you build this individually, then you will not be able to leverage their similarities, because they're all reviews, although they're different, but they have similarities, so they can transfer knowledge from one domain, from one product to another product. Okay. So in this case, we want to continually learn. For example, today I want to learn how to classify the reviews of TVs. Next day I want to learn about the VCRs. Next day I want to talk about refrigerators. Okay, learn all these things. How can I continue to learn this thing? And traditionally, we just say, okay, can we just use fine tuning? This bird is a language model, and then we'll see it performs very poorly. Okay, very poorly, and which basically because of forgetting. Okay, the reason is when you do this bird type of thing, you essentially capture something very specific, and when you capture something very specific, then those specific stuff is very hard to transfer. Okay, so when you learn the next one, then you basically you don't gain anything, and you also possibly destroy what you learned in the past. Okay, so in this case, we are using the adapter, which essentially adds something to the bird. So essentially, this, you can see this adapter add in the middle. So we don't want to destroy the bird's the trained parameters. It just add some adapters. So this adapter idea come from natural language processing. This is not our idea, but in this case, we just borrow this thing to our for our continual learning. Okay, so adapter essentially is a two feed forward layer, and with a skip connection. But we have to change this because we want to learn continuously, and obviously we have to add some more mechanism to do the protection, and also for knowledge transfer. So in that case, we call this sort of a plug-in, the second part of the CLA. Okay, CLA, which is more complicated. Okay, more complicated. I will explain that. Okay, explain that. So this is based on capsule network. It's basically based on the capsule network. And then we have two level of capsules. So the first level of capsule essentially for each task with some capsules. So the bottom part you can see is the input. Okay, input. And whenever we have a new task, we are going to create a new capsules. Okay, new capsule. And then when we have the capsules, we're going to this output will go to the next level. Okay, go to next level. And that will be the knowledge sharing level, because we want this different task to share some knowledge, so I can transfer the knowledge to the future and to the past, and to make everybody performs better as we see more and more domains, or more and more products. Okay, reviews. So the knowledge sharing, how does knowledge sharing happens? So what happens is when you have the data goes in, and this capsule network has something called dynamic routing. So what that means essentially, it says those things which are similar will go to a capsule in the next level, which sort of agree with this guy. So essentially, it's a little cluster. It's just say, oh, all those guys are similar to each other. Okay, when they're similar to each other, then obviously they have lots of shared knowledge. So through this dynamic routing, and we can send things to the next level capsules which contain similar kind of stuff. Okay, we have a different type of capsules, and each of those contains things which are similar. Okay, similar. So that's essentially the idea of knowledge sharing. And then we go to the next level, is a task specific module, which is essentially trying to say, okay, now I need to protect myself, because you learn some knowledge, but now we want to do the classification, but I also do not want you guys to sort of conflict with each other. Sort of you're gonna forget, you're gonna interfere with each other. Okay, interfere with each other. So now I'm going to have this mask to protect each tasks. Okay, so I say you already learned the shared knowledge, and then now I say for the TV reviews, you learn something, I'm going to protect you. Okay, for the VCR, I want to protect you as well. I can protect you as well, and then you keep doing more and more, and I somehow protect you so you don't forget, you don't get sort of interference with each other. Okay, because when those things goes to the next level, they all mixed up together. So although at the middle they are sharing something, and it goes up, they got mixed up. So we need protection. So with this sentiment analysis, and we have 19 kind of products, and then each of these products has a lot of reviews. And for each of those sentences, we want to classify what is positive about something or negative about something, or has no idea. So basically a neutral. And then we compare with a lot of baselines. Some of the baselines we create ourselves. Some baselines are existing systems. They are not really existing systems in the natural language. Most of the systems are sort of for computer vision, and then we convert them because in the natural language there's no system does this. Okay, no system does this. So we convert those systems for computer vision to this to handle natural language, and then we compare the result. So you can see, and we can make quite a bit of improvement. Especially when we talk about MF. This is the macro F1 score. Okay. So next thing I'm going to talk about is the post training of a language model. So I assume most people are familiar with language models. You probably heard of BERT and Roberta, and then you heard about this the GPT-3, GPT-2, all this kind of stuff. There are many of this BART, this kind of language model. And language model has been quite sort of instrumental for natural language processing. With those language models now, as the feature extractor or whatever for the generator, you can produce much better sort of end task. For example, you want to do classification or those things, and this give you very good sort of features for you to perform your end tasks. However, the language models they can get outdated. Okay, and the first question is first issue is it can get outdated because, for example, some of the language model was trained with text from 2 years ago, okay, or 3 years ago, and then obviously you will not be able to deal with the COVID-related documents. Okay, when I say COVID, but this guy will not give you something interesting because the COVID was never seen it before. And also this model sometimes they cover everything, and then they are very general, but they may not be good. They may not be perfect for a specific domain. Okay, so now we want to use a specific domain to fine-tune this model. Essentially, it's not fine-tune. We normally call that sort of adaptive pre-training, and we also call it post-training. So we want to improve this model for a sequence of specific domains. Okay, and we post-train already trained pre-trained language model. Okay, and for example, in this case, we use Roberta, and this is a very strong pre-trained language model. Okay, pre-trained model. We want to add more capability to this guy. So essentially, we want to adapt this thing to some new domains or to something domain which are not necessarily covered very well. Okay, and then we want this guy to learn incrementally. So in this case, it's an unsupervised task. So the domain corpus and the corpuses are not really do not have any labels. So of course, when you do the training, you can make this self-supervised kind of thing, And then we also deal with some when we do the masks, and we have to deal with some kind of very strange things called we call the butterfly effects. Essentially, something small change you can sort of destroy the model. So we're using sort of adapters, but in this case we're using the parallel adapters. So you can see the difference. In this case, the CL plugin is parallel to the language model. Okay, you can see the previous one, they actually is inserted in the language model. Okay, so in the language model, so it's serial. So in this case, it's parallel. Okay, this does better. We tried it. Does better. Okay, that's better. So the idea is similar to the previous model, but this is a sort of it's outside. And another thing is this butterfly effect. And if we want to protect what we learned in a particular domain, and then this is going to be this protection is not exactly complete 0 and 1 kind of a gate. It's not a step function 0 and 1. So there's a little bit of things which still allow the gradient to flow through. Okay, to flow through, and that when we're doing this thing, we find wow. And later on, when we do the end task, fine tuning the end task, then this causes a lot of trouble. It causes a lot of forgetting, and then we sort of we fix that. Essentially, we use some kind of threshold to fix that and to make it work. And now you can see this. You can see basically you are no forgetting, and pretty much no forgetting. And here is also some results. And I think I'm going to move on. Okay. So this last part of the topic, I'm going to talk about this learning on the job after deployment. Okay. So so far we are talking about this continual learning, especially this three topics. Okay. One is talking about CL, and which is quite general, it's more theoretical. And then we talk about these two applications, not applications, but they are sort of an NLP kind of continual learning. And then what is the key characteristic is the data and the task are all given by human beings, or by engineers or whatever. So those things are given. So you give me a new task, you give me the data, I learn it. Okay, but that's not the case in real life. Okay, in real life, and when you go to work, and for example, you do a self-driving car, you drive on the road, and then you cannot expect, on the road somebody giving you something, and then you sort of learn on the road. Okay, so you have to detect, the algorithm itself has to detect what sort of new task which you might be facing, and then you learn that task by yourself incrementally. Okay, on the job. Okay, sometimes we say on the fly. Okay, on the fly. So this is what do we mean by learning on the job? And this is from social science. It's estimated about 70% of human knowledge comes from on-the-job learning, and only 10% through formal training or education. Another 20% come from sort of imitation. You see other people do this, and then you learn how to do this. And then how do we do that? And we basically propose this model, which is called self-initiated open world continual learning. Okay. So self-initiation is important because everything has to be sort of initiated by the system itself, rather than by engineers or humans or the user. Okay, you basically figure out what the stuff you don't understand, and how do you learn to understand it? How do you learn to understand it? All right. So here's an example. It's a greeting bot in the hotel. So for example, we have a hotel, and then we have the robots roaming around in the lobby, and basically greet the customers, the guests. And then, for example, this bot sees an existing customer, say, "Hey, hello, John, how are you today?" Right? And because the bot knows this person, can recognize this person. Okay. But what happens if it sees a new guest? So this bot is supposed to recognize this person is new. Okay, if it's new, then this bot is going to say something else. For example, bot will say, "Oh, welcome to my hotel. What's your name, sir?" Okay. So how does this system detect this person is new? So that essentially is the task of out of distribution detection or novelty detection. So this person is novel. We want to detect this person. And this also creates a new task. What is the task? Basically, we need to learn to recognize this person. Okay, so this is a new task. So when the boss says, "Welcome to our hotel, what's your name, sir?" So essentially, the person you're trying to get the name of this person, and also you're trying to get the class label of this person. So this person probably will give you, say, "Oh, David," for example, "my name is David," something like that. And then you pretty much get the class label. So this object, this person or object has the label of David. Okay, so in this case, now you can sort of take some pictures or whatever, and you get training data, right? Because the person is just in front of you, right? You can take some pictures, and then you can learn to recognize this person. okay, incrementally. So you don't destroy, okay, what you've learned in the past. You recognize a lot of other things in the past, but now you, in addition to those things you have learned in the past, and now you learn a new person, which is called David. Okay, so next time when David shows up, and you can say, oh, hello, David, how are you today? Because, you know, you learned it. So you can't say, you know, you don't recognize this guy anymore. Okay. So you can see this process is completely sort of self-initiated, and it's autonomous. So there's no engineer involved. Of course, there's a person involved because the David, right? David is person, and then you have this interaction. But this interaction is very natural. It's completely free. You don't need to pay any money, because when you want to label data, then you have to pay somebody to do the data for you. So this is a very natural kind of a process of learning and using knowledge. So how can we do this to get the real system to do this? Okay, there's complete autonomy. Okay, complete autonomy. However, this is a very difficult task, because in the real hotel, the situation is much more complex. Okay, and then the bot, you know, how do they know this is a person, or maybe it's the animal, or maybe a piece of furniture? How do you recognize this thing is a person? So, and even you recognize something, then you have to characterize it. Okay? You characterize it. You know, is it the animal, or is it a sort of a piece of furniture? Is a person? If it's a person, it may not be a hotel guest. It could be somebody come to have a dinner here, or it may be a policeman. So when you have different characterizations, you're going to have a different kind of sort of response, right? For example, you see an animal, you probably go to report to the hotel employee. If the policeman, you better don't do nothing. And if you see somebody carry the luggage, you might say, oh, this should be a guest. And then you can say, welcome to a hotel, and what's your name, sir? So this has a lot of components. It looks like my time. How much time do I still have?
7 minutes.
10 minutes. Okay, and I should try to finish in 10 minutes.
6 minutes. I'm sorry.
Oh, 6 minutes. Okay. I need to hurry up. So essentially, this is going to be a complex system. So let me just go through here. Okay. So there are lots of components. So we have this continual learner, and then we go to the model, and also we must make sure when we recognize something novel, we need to know this is relevant. Okay. If it's not relevant, then we don't want to worry about it, because, for example, we are doing this greeting, and then if you give me something, if it's something like a furniture, then I don't know, it's not related. Okay, so I'm not going to say anything. And then you have to characterize it. You have to adapt it. Okay, how do you behave after you see something new? And in the process, you have to worry about the risk assessment. Okay, sometimes it can be risky. For example, if it's a self-driving car, if you do something not quite good, then it can be very risky. And also have the interaction model. And this is essentially say, how do I interact with the environment or with the people? Okay, and then to get the knowledge, and so I can learn that myself, and in the future I will not have problems. Okay. So now let's just give you an example. We have a little system, which is a system for chatbots. Okay, for chatbots. So the performance task is just something like in the Alexia or series, and I issue a command, and the system basically performs that command. For example, I say switch off the lights in the kitchen, and the system basically does it. Of course, the system needs to understand what I'm saying. Okay, so we build this system, and what's the idea? The idea here is it's a very simple system. We say, I save some commands. So normally I know how do people say switch off the lights in the kitchen, right? I save something, and then when somebody new come to say this thing, I can do the match. So I know what I'm supposed to do. Okay, what API action I'm supposed to do. So we call this a seed command. Seed command. Okay, so essentially it's just a paraphrased commands. Okay. And also we want to learn continually. For example, I say something the system does not understand, and then the system should interact with me and learn what I mean. And the next time the system will not have problem. Okay, essentially this is a lifelong learning dialogue system or chatbots. Okay, chatbots. So what do we mean by something saved? Okay, something saved. And the seed command means So this API action, you can see this table on the right. So this API action is a switch on the lights at a particular location. So normally people say switch on the lights. The X means the variable, essentially the location you can get from the utterance from the user's command, or put on the lights. So many ways to say this. So this is what we saved. Okay, it's just an example. You say, switch on the lights in the bedroom. Okay, switch on the lights. So so let's let a particular SC like this. This is things put on the light, which is here. So when the user issue a command to power on the lights in the bedroom, and then the system will understand it, because of course we have some things to, although they are not exactly the same thing, but we have something to make this thing match each other. Okay, match each other. So the variable x1 will be the bedroom. Okay, and that system will basically be just switch on the lights. Okay. So what do we have in this case? We have seed command specification. Essentially, we allow user to specify this kind of stuff, because when you have an application, normally you have the API actions. Your API actions and what exactly those functions are, and then you basically put some sort of write some sort of initial seed command. And then we have a specification language that allows you to do that. And then we have the ground module, command grounding module, which is basically say, okay, when you have this, and my command is like this, and how do I sort of do this matching? Can do this matching. And the next one is a continued learner. And when the system does not understand what the system do, okay, what the system do. Okay. So in this case, of course, if we come back to this novelty detection area, this kind of thing, and we have this novelty detection. Where's the novelty detection? Actually, the learner itself does novelty detection. So this guy, open world learner itself, does the novelty detection. And so in this case, what do we mean by novelty detection? Essentially means when the system does not understand something, which basically means it does not match anything. For example, this person says, turn off the lights in the kitchen, and the system could not find anything to match. Okay, so basically, I don't know what to do. Okay, and so in this case, we know the system has to learn. Okay, the system itself knows it has to learn. And then how do we do this characterization? Okay, this is something new, characterize it. So in this case, you will know, system need to know, okay, and which part I understand, which part I don't. For example, the system understands the lights in the kitchen, but has difficult to ground this turn off, because in this case, there's nothing turn off, right? The switch off, turn off, that looks quite different. You don't know what to do. Okay. So the system knows the kitchen, but don't know turns off. So this is the characterization. So based on this characterization, the system will communicate. We basically have a communication with this user. So the user will basically, this is essentially the response. So when you have the characterization, then you have your planned action. What are you going to do next? So essentially, the system will have this communication with the user. And then the system may say, "Oh, sorry, I didn't get you. Do you mean switch off the lights in the kitchen, or switch on the lights in the kitchen, or change the color of the lights in the kitchen?" So you can see this is pretty much restricted. So the system understands lights in the kitchen, but it's the front part does not understand. And then the system, the user may just say, "Okay, just basically the first one, switch off the lights." So you can see this becomes the ground truth for the previous for the command to turn off the lights. And then system can learn this thing. So next time when the user says turn off the lights, and this particular user or some other user say turn off the lights, the system will understand. Okay, this is completely automatic, learn it by itself, with the interactions. And also we need to assess the risks. Okay, so in this case, we don't want to, the first one is we don't want to ask the user too many questions, because you don't want to annoy the user. Okay, and the second thing is your characterization, if you are not so confident, okay, and so there's two options. If you are not confident, you basically say, okay, I don't really know what you're saying, so I can give you all the possible commands to give you, and then let you tell me which one you mean. But this can be very long. So in this case, you better be careful. You should take some actions which is not going to annoy the user. You may say, want to take the action, say, okay, why don't you just say the same thing in a different way, right? Because first you say turn off the lights. I don't understand. Can you say in a different way? And so that is okay. But if you give the whole list, then the user will know, oh, this is a junk system. It doesn't understand anything. Okay, that doesn't understand anything. And also sometimes very long, it's difficult for user to even to remember to choose. Okay, so this is the risk assessment.
I'm sorry to interrupt you, but we need to finish. Can you
I'm done.
finish the session in 2 minutes?
Yeah, I'm done. This is a summary.
Okay.
Okay.
Thank you.
Okay. Yeah. And so essentially, let's just try to summarize to make the agent to be more intelligent and autonomous, and we need to make the system to learn continually, and also not just before, but also after deployment. Okay, after deployment. Okay, and obviously this is a very sort of a new area, and this is a DARPA project. Okay, the DARPA project. And there's lots of challenges, okay, lots of challenges, but I believe, and some of those things can be applied in real life kind of applications already. All right, thank you very much, and just thank some of my collaborators and also the funding from DARPA, from National Science Foundation, and the Northrop Grumman. Thank you. Any questions? I'll be happy to answer.